16 here. There are three main points that I want to talk to you guys about in chapter 16. All right. The first point here is what's called the common ion effect. This is something I'll go over. All right, the second thing that we'll talk about and I'll teach you in this chapter are acid-base titrations. Okay, so you guys should know titrations because you did a lot of titrations in the last week's lab, but these are acid-base titrations, so a little bit different. This is your problem set that you're doing this week and next week. Okay, a lot of problems in that set. Okay, I'll talk briefly about buffers, and then the third and final thing about this chapter is a new K, a new equilibrium constant. This is called KSP, and this is called the solubility product constant. Okay, we did this last week in our lab. In our lab, we had to calculate the KSP of calcium iodate. All right, let's first go over the common ion effect. All right, so I'll go over this briefly. All right, so chapter 15 was entirely about weak acids, and one of the common weak acids is an acid called acetic acid. Okay, this is acetic acid, and this is the Ka for acetic acid. All right. This is acetic acid. It donates a proton. It gives you H plus and the conjugate base to the conjugate acid, acetic acid. All right, so this is a weak acid. How do I know it's a weak acid? It's not one of our six, and it has a Ka. I'll give you the Ka, okay, for acetic acid. I'll give you the Ka for any weak acid, and it's 1.75 times 10 to the minus 5. All right, so we use the ICE table. We can use the low ionization assumption. You do all those things to calculate the pH of a bottle of acetic acid. All right, now we're going to add a little twist to this. Okay, the twist is this. I am going to take to that acetic acid, to that acetic acid, we're going to add some sodium acetate to it. Okay, this is sodium acetate. Now, sodium acetate actually dissolves in water to give you acetate ion and sodium ion. Okay, but if you take a little bit, 1 gram or however little of sodium acetate and put it in here, what happens is that you have a common ion. So what is this common ion? You add some sodium acetate to this bottle of acetic acid. You have two common ion. I have one common ion. Okay? That common ion is acetate here and acetate from this reaction. Okay? So we're going to call acetate the common ion. And what the common ion does, this is really the take-home point. The common ion does is that it's going to suppress ionization. It's going to shift the equilibrium. Okay, equilibrium, look at the arrows. It's going to shift the equilibrium away from the ions, and in this case, that is the left. Right, so take some sodium acetate, add acetic acid, it will shift to the left, and the common ion here is acetate. And the equilibrium will shift to the left, and it's going to essentially suppress ionization. Okay, so can we associate these two words, common ion effect, with suppressing ionization? Okay. link those two or memorize this or understand that if you have a common ion, when we go over these problems together, okay, it's going to go to the side away from the ions. It will go to the side away from the ions. In other words, it will suppress ionization. Okay, it will suppress ions. Okay? In this case, the common ion is the acetate ion. The equilibrium will go to the side away from the ions. In this case, that is left. This is like Le Chatelier's principle. Okay, like Le Chatelier's. Common ion suppresses ionization. Okay, take home point. Common ion suppresses ionization. I want you guys to know that. Equilibrium will be to the side away from the ions. All right, so now let me tell you another thing here. Okay, there is a lab we did. I'm going to move on to page 2 here. There's a lab we did last week. It was kind of a long lab. We did a bunch of titrations. But what we were doing is we were trying to identify a new equilibrium constant. And this equilibrium constant is called KSP. Okay? Solubility product constant. So what you did in the lab last week, which I'm going over now, formally in our lecture, okay, you had calcium iodate, which is a solid. Remember, you took that solid, you split it into 3 parts. One part in case you mess up. The other part you put it in 80 mils water. The other part you put 40 mils water. Well, when you put it in the water, 80 mils or 40 mils, this calcium iodate actually is in an equilibrium with its ions. And it's in an equilibrium with the calcium ion and the iodate ion. Okay, we always balance it, so we'll put a 2 here. Okay. So look at my arrows once again. So this is a KSP. The solid is in an equilibrium with its ions. Okay. So KSP is when a solid is on the left-hand side, and we call these solids sparingly soluble solids. It's another thing I want you to link together. Okay, so sparingly soluble solids. So sometimes the solid can go back into its ions. Okay, this is KSP. So what is the expression for KSP? Okay, products over reactants, but we don't put a solid in there. Okay, we don't put a solid. Why do we not put a solid? Because solids do not go into the equilibrium. All right, so this has some value. You could look at some of the KSPs on page 18 of our notes. So 18, I think. Or no, not 18, 16. Anyways, there's a table in our notes of all the KSPs. I'm not finding it now, but yeah, page 12. So I'll give you the KSPs, okay, for the solid. Okay, how do you write the equation? Okay, the solid is going to the ions. Okay, why did I put a 2 here? Why did I square this? Because there's a 2 here. Okay, so remember the formula for the law of mass action. Okay. All right, so solids that sometimes go back, but sparingly. So they're sparingly soluble solids. Okay, check my states. The solid can go back into the aqueous state. This is what you were doing in the lab last week. You were trying to find the value of the KSP. All right, here's another one. Calcium fluoride is in an equilibrium with calcium ions and fluoride ions. Okay, what's the KSP for this? F minus squared, good. Divided by calcium fluoride? No, because it's a solid. Okay, good job. All right, so this has a value 4.0 times, I can't read that. Anyways, I'll give you that value, 4.0 times 10 to the minus 11. Okay, that would be for calcium fluoride. Okay, I'll give you these KSPs. I'll give you them. Okay, because every sparingly soluble solid will have a KSP. All right, what happens if I add calcium nitrate? Okay, all nitrates are soluble. So what happens if I add calcium nitrate here? Any, like 0.2 molar or whatever molar. Okay, what happens if I add calcium nitrate to this and to this? Okay, remember calcium nitrate is calcium ion plus nitrate ion because they dissolve in water and break up into the ions. So what happens if I add a little bit of calcium nitrate to this calcium fluoride? What happens if I add a little bit of calcium nitrate to this calcium iodate? Common ion. What's our common ion here? Calcium. And what does the common ion do, Susanna? It suppresses ionization. Okay? So adding the common ion, in this case calcium, is going to do what? Okay. Believe it or not, it's going to make more solid. Okay? Suppresses ionization, reducing solubility. Believe it or not, adding calcium ion here, okay, will make more calcium iodate, make more of the solid, suppresses ionization, reduces solubility. Okay, so
Is this just Chandler's principle?
yes, correct. But they formalized it, Sam, as the common ion effect. Okay, it's called the common ion. Very good. All right, so common ion effect. I want you to associate this with suppression of ionization, and then we introduced a new K here, KSP. All right, I'm going to take an aside here. I just remembered for your homework, I'm sorry, not your homework, your lab, the lab with all those practice problems that you can work together on, you can skip KF problem. Okay, so there's something called complex ions. Complex ion formation, you can skip those KF problems. I'm not going to go over that. We're already behind, so you can skip KF on the lab problem set. So, back to lecture. Okay, you can skip any type of KF problem, so don't do it, and don't have your lab partners do it. All right, so KSP, common ion effect, suppresses ionization. We learned a new K. Actually, let's figure out how many Ks we learned here. Okay, so we have Kc for concentration, Ka for acid, Brunstad acid, Kb for base, Kw for water. Okay, if we're talking about gases, sometimes we have a Kp, and now we have a KSP. Okay, I'm not teaching you KF. Okay, sorry. It's a lot of Ks. Okay, all of them are products over reactants. And which K involves the sparingly soluble solid? KSP. Okay, solubility product constant. Okay, let's move on here to the next part. All right, this is the Henderson-Hasselbalch equation. so we teach this in Gen Chem 2, but this has a very interesting history. So allow me to tell you a little bit about the history. Henderson and Hasselbalch were actually doctors, medical doctors at Harvard Medical School. So they were physiologists. And I think to this day there's a Hasselbalch Hall. You know how we call this Hendricks Hall, Hendricks Science Complex? There's a Hasselbalch Hall. And they were physiologists, and they were studying whatever, medical physiology. And they taught at the medical school. These two became famous for developing a formula. This is called the Henderson-Hasselbalch formula. I'll give this to you on the exam. Okay, so I'll write out the formula. I used to derive it when I first was teaching this course, but now I'll just give it to you, and you can use it for the test. Okay, so it's going to be pH equals pKa plus log. Okay, if you ever need to, if you're ever in a situation, or a situation arises where you need to memorize this and you don't know what to put into what, okay, you just remember drop the acid. Drop the acid. Okay, drop the acid means put the acid in the denominator and the conjugate base goes in the numerator. So drop the acid in case you're, confused on where to put it. Okay, drop the acid. Right. Anyways, I'll give this to you on the test, and it's pH equals pKa. Don't forget pKa is the power of the Ka. Okay, plus the log of the conjugate base over the conjugate acid. Okay, where do we use this? We use this for buffers. Buffers. Right, so now I want to talk very briefly about buffers. So if you see a buffer, you're going to use this equation. How do you know you have a buffer? Okay, you know you have a buffer because in the bottle, in the solution, what two components you'll have? You'll have the weak base and the weak acid. Okay, so a buffer is a combination of a weak acid and its conjugate, weak conjugate base, weak acid. The acid-base pair, the conjugate. So it's a combination of weak acid and its weak conjugate base. And this serves a purpose. And the purpose of this is that it will keep, within reason, it will keep the pH steady. Okay, avoid fluctuations in the pH. Avoiding pH fluctuations. So how many of you are biology majors again? There's a lot of bio majors. So you may have heard of buffers. Have you heard of buffers? Okay. So a buffer keeps the pH steady. You want this inside your body, like your blood or inside of a cell. Usually the pH inside the cell should be around 7.4. Okay. If the pH goes below 7.4, it's a disease called acidemia. And then if it's above 7.4, there's another disease. It's just too basic. So your body wants to keep it within the 7.2, 7.4 range. The best buffering capacity is when the the pH is equal to pKa plus minus 1. That's when you have the best buffer. Okay, pH is equal to pKa plus minus 1. Okay, if you can get your pH to the pKa of the acid plus or minus 1, this is the best buffer. It can withstand the pH within plus 1 pH unit plus minus 1 pH unit. All right, so let's step back a little bit here. Okay, buffer keeps the pH steady, okay, maybe plus 1 or plus minus 1 pH unit. Can't go too high, can't go too low. There's a lot of health implications for this. And we'll use this equation, the Henderson-Hasselbalch equation, in the applications of buffer, or for the application of buffer. Okay? How do you know when you have a buffer? What two things are in there? It's just a weak acid with its conjugate. Okay, very good. Okay. All right, let's. Our standard weak acid is acetic acid. Okay, and if we put in some acetate in here, like some sodium acetate, we have established a buffer. Okay. So let's say I add a strong base in here. Okay. What will the okay? It's like maybe not so concentrated, but I'm not giving concentrations here. But let's just say you put a strong base in here. The strong base will get neutralized by the acetic acid. Okay. Let's say I put a strong acid in here, like an HCl or the 6 strong acids. Okay, that will get neutralized by the acetate ion. So within, certain concentrations that are not too concentrated, this combination of acetic acid and sodium acetate can neutralize the effect of a base and at the same time neutralize the effect of the acid. Okay, so this is what a buffer does. Okay. Can a buffer have H plus, strong acid, or OH minus in there? Okay, very good. No. Why is that, Sam? Do you want to guess?
It needs to be, it's going to dissociate all the way.
Right.
Unique to be a buffer.
Because strong acids, what do strong things do? They eat everything up. Okay? So let's say we flip this. Okay? Let's say we instead, first of all, this is not going to happen because this cannot have a buffer. Let's say we have HCl and NaOH in here. First of all, this is not going to happen, okay, because this and this cannot serve as a buffer. Okay, but let's say we have HCl, our strong acid, and NaOH, our strong base. Okay, you add CH3COOH, you add acetic acid. Okay, what will happen? Okay, this will devour it. It just swallows it up. Okay, let's say you add a little bit of the weak acetate, the weak conjugate base. Okay, this acid will devour it. Okay, so when this devours this, okay, because strong does that, and this devours that, okay, your pH is going to change. Okay, this will devour this. Okay, so what you'll have is a whole bunch of COOH. This will devour that, so what you'll have in here is a bunch of CH3COO minus. And the net effect of all of this is that your pH will go up or go down. Okay? In fact, the strong acid will make the pH go all the way down. The strong base will make the pH go all the way up. If they're in the same concentrations, they neutralize one another, and you'll get to a pH of 7. Okay, that's, yeah. Okay, you add the weak acid, okay, your pH will go down. You add the weak base, the pH will go up. Okay. All right, So anyways, maybe I meandered a little bit here. The take-home point is this. You don't want strong acid and you don't want strong base. They cannot serve as a buffer. Why? Because the strong acid will totally eat up the base, and the strong base will totally eat up the acid. Okay? So no strong acids, no strong base in your buffer. The only good buffer is a weak acid and a weak base. Okay? So just remember that. So the best buffers are the weak acid and its conjugates. All right, I will explain this better when we go over some titration problems. Okay. For now, just realize and recognize buffers need to have weak acids and weak bases. All right, let's move on here to page 3. All right, so what is the pH of a 0.3 molar solution of formic acid? Okay, do we know how to do this if I give you the Ka? Okay, we should know how to do this for our test that's coming up whenever it comes up. Okay. First thing is you're going to write the equation. For the Ka. All right, I'll give you the Ka on the exam. Which is 1.8 times 10 to the minus 4. It's a weak acid, so we'll do our ice table. We don't care about liquids. This is 0.3 molar. Okay, so this is something we should do on our test. Okay, plug it into the Ka. Because remember, Ka is equal to H3O plus HCOO minus divided by HCOOH. Okay, so plugging those equilibrium constants in. Okay, next thing you want to do for your quiz, test, homework, at least in my class, there's no quadratic, so we can do the low ionization assumption. We assume X is small. All right, and then we'll solve for X. So once we do that, I'm just going to really quickly do this. So I'm hoping that you guys are comfortable in doing this. So I'm getting 0.00735 molar. Okay, that's X, but what does X symbolize? Okay, it's this X and this X, and that symbolizes the concentration of H3O plus. And then so we have our pH is equal to minus the log of H plus, which is minus the log of 0.00735, and that will be our answer. Okay. 2.13. So that's all well and good. Hopefully you're comfortable doing that. We've done a lot of those. But let's look at part B for a second. Okay, 0.3 molar formic acid, and now we're going to add 0.52 molar potassium formate. Okay, potassium formate. So what is the common ion here between potassium formate and formic acid? What is the common ion? Okay, so in part B, we're adding some potassium formate to this. So what is the common ion? Okay, so this potassium formate is formate ion and potassium. And then we add it to this, so what will be our common ion? Okay, what's common between this and this reaction? Okay, this is potassium formate, so we add it to this. So what's the common ion? What's the common ion here? Okay. Common ion is formate. Okay, formate. Alright, so in part B we add 0.52 molar potassium formate to 0.3 molar formic acid. What's the common ion here? Okay, formate. Okay, so we're adding more formate, which is HCOO minus. This reaction already has formate HCOO minus, so what will the common ion do? It will suppress ionization. Okay. So what we can do is we can actually do another ice table, okay, with in part B with our 0.52 molar and 0.30 molar, but what do we have in our solution? Okay, we have formic acid, and what else do we have? Formate. Okay, so we can use the Henderson-Hasselbalch equation. We also have a buffer. Okay. All right, the buffer consists of formic acid and formate. So instead of doing an ice table here, let's use this equation. pH is equal to pKa plus log. Okay, drop the acid. And then the conjugate base. Okay. So what is pKa? Okay, it's minus the log of Ka. Okay, so what is Ka in this problem? It's going to be 1.8 times 10 to the minus 4. Okay, what's the concentration of formic acid in this problem? Okay, it's 0.52. What's the concentration of formic acid? Oh, I'm sorry, the concentration of formic acid here is 0.30. I'm sorry. Okay, what's the concentration of formate in the form of potassium formate? Okay, 0.52. All right, so this is what we'll put in our calculator. Okay, so log of 0.52 divided by 0.30. Plus minus the log of 1.8 times 10 to the minus 4. Getting about 3.98. Okay, 3.98. So instead of doing an ice table, okay, you can use this equation. When do we use this equation? Okay, when you have the conjugate base alongside the acid, its conjugate acid. Okay. You have the conjugate base alongside the conjugate acid. All right, that's when you use this Henderson-Hasselbalch equation. All right, how about this one here? Calculate the pH of 0.2 molar solution acetic acid. All right, so the Ka for acetic acid is 1.75 times 10 to the minus 5. I'll give you that. Okay, do we know how to do part A? Shall I do it, or do you want to do it at home or by yourself? Can we do this? All right, what's the first thing you'll do? What's the first thing you'll do? Okay, the first thing you'll do is write the equation. So what is this equation? Okay. This will donate a proton. Okay, what's next? Start your ice table. Very good. All right, so we have 0.2 molar. Okay, what's next, Susanna? Okay, we'll plug it in, right, to the Ka, which is products over reactants. So x times x is x squared divided by 0.20 minus x is equal to 1.75 times 10 to the minus 5. Okay, so I'll give you that Ka for acetic acid. All right, what is next here? Okay, we'll use our what assumption? Yes, we'll assume x is small, so that 0.2 minus x is about 0.2. So we'll solve for x here. Okay, so what will x be? What's 1.75 times 10 to the minus 5 times 0.2? Square root that. Square root that product, we're getting 0.00187. Okay, molar. Okay, but what does that X really symbolize? Yes, CH3COO minus acetate and H3O plus. Okay, so pH is minus the log of the H3O plus. Minus the log of 0.00187. And what is that on our calculator? About 2.73. This is the answer I am getting. All right, so that's part A, because you see the bottle of acetic acid. It does not just contain acetic acid. Okay, this bottle of acetic acid. What else is in this bottle of acetic acid? Okay, besides water, everything is dissolved in water. Okay, some of this acetic acid contains acetic acid, but it also contains proton and acetate ion. All right, so let's go to part B. 0.2 molar acetic acid with 0.3 molar acetate. Okay, what do you think we have here? Okay, if this is the acid, what will this be? Its conjugate. So we have two parts here. What do we have? The acid and its conjugate. We want to calculate the pH. So what equation can we use? The Henderson-Hasselbalch equation. Okay? The Henderson-Hasselbalch equation. So let's go ahead and do that here for part B. Okay, in case you ever want to know which goes where, drop the acid. In this case, our acid is acetic acid. Drop the acid, so it goes in the denominator. And up top is the numerator. Okay. So pKa is minus the log of Ka. Right, I'll give you that Ka. It's 1.75 times 10 to the minus 5. That's pKa plus log the acetic acid. What is the acetic acid content here? 0.2. And what is the acetate, Susanna? It's correct. All right, everyone see that? All right, let's do this on our calculator. Minus the log of 1.75 times 10 to the minus 5. About 4.76. Okay, plus log of 0.3 divided by 0.2, that's 1.5. Okay, so log of that is plus 0.176. I'm getting about 4.94 is my answer. Okay. 4.94. So acetic acid by itself is 2.73. You add some acetate ion, it's a buffer. Acetic acid and acetate would make it a buffer. Your pH goes up to 4.94. You notice you add 2.73, you add a little bit of the base, the conjugate base, the pH only goes up 1.2 units. 1.2 units. Remember, the best buffering capacity is when pH is pKa plus minus 1. So you add a little bit of base, the pH only goes up 1.2. Okay, so a really good buffer in the sense, a weak acid with its weak base. All right, so let's just wrap up some points here on buffers. I think, like I mentioned before, strong acids and strong bases do not have a good buffering capacity. Okay, you don't want anything strong there. And then what does a buffer do well? A good buffer will keep the pH steady. It keeps the pH level. Okay. All right, our next major topic here is titrations. So, you guys know what a titration is. You guys have done them in Chem 1. You've done several of them in Gen Chem 2. I think you'll do a lot if you take analytical chemistry. But basically what you have here in the burette is the titrant. And then here at the flask is the titrand. Okay. The burette, you can control the amounts of titrant that you add to the titrand. Okay, once the titrant equals the titrand, that's the equivalence point. Okay, when they equal one another, this is called the equivalence point. Okay, so there's basically 4 phases to a titration. Okay, phase 1. Okay, we're going to do, so this can be a strong acid or strong base, and this could be, that's in the burette, and this could be a weak acid or weak base, that's in the flask, also known as the titrand. So we'll have different combinations that you can have here. Okay, but there's 4 phases here. Okay, the first phase, let's say there is no acid added. Okay, or base. Okay, 4 phases. That's phase 1. We'll do a problem like that. That's part A. Part B is you start adding acid or base. Okay, from the burette. Okay. Phase 3 is you add acid or base to reach the equivalence point. I'll call it EP, equivalence point. Okay, where the titrant now is equal to the titrand that's sitting here in the flask. So that's phase 3. And then phase 4 is that you have excess acid or base, okay, beyond equivalence point. Okay, that's phase 4. Okay, so the first phase, nothing is added. Okay, you just have the acid or base here. The second phase is before the equivalence point. Okay, the third phase is at the equivalence point where you add enough titrant to equal the titrand. Okay, that's usually when you have a color change, the equivalence point. And then the last phase is that you are beyond the equivalence point. Okay, so these are the 4 types of titration problems. Okay, nothing is added, no titrant is added. You add the titrant, but it's before the equivalence point. You add enough titrant so that you're at the equivalence point, and then you add a little bit more so that you're beyond the equivalence point. So in part A here, this is what we'll start on Friday. Okay, in part A, this is, we're not adding anything. Okay, so no titrant added. Okay, part B is before equivalence point. Okay, part C is the pH at the equivalence point. And then part D here is after or beyond the equivalence point. So that is what we will talk about on Friday. So we'll have a titration problem to do. We'll do some titrations Friday and probably wrap that up on Monday. Do some more KSP problems next week as well. All right, so I'll see you all on Friday.